Hello. For the Robotics Research Project module, we've been working on a sensorized wheel spoke design for the NASA Perseverance rover. The limitation of the current Mars rovers, Curiosity and Perseverance, is that they rely almost entirely on cameras for terrain assessment. They can spot rocks and slopes, but cameras cannot detect ground softness, loose soil, or subsurface hazards. We saw the consequences of this in 2009 when Spirit rover became permanently stuck in soft soil that looked safe from above, a mission-ending failure. Neither of the current rovers have any force or torque sensing at the wheel. Our objective was to try to fix this by embedding strain gauges directly into rover wheel spokes to classify terrain mechanically from the vibrational responses as the wheel drives over it. We attempted to achieve this by slightly modifying the cross-sectional area of the spoke to try and isolate natural frequencies for enhanced readings from the sensors.
So we're focusing on strain gauges with this project, but why are strain gauges so useful? The main reason is they have complete data coverage, capturing both static baseline loading and dynamic frequency changes when piezo sensors can only do frequency changes. So we get a full picture of what's happening to the wheel spokes. They're also highly suitable for aerospace applications. They're immune to vision blinding, and they offer near zero mass and power cost. They can also have extreme temperature resilience if they're specialized. They have the potential for spatial filtering using strain concentration points to isolate specific frequency bands, which is something we're exploring, and this could reduce the compute cost of machine learning processes. Our configuration of choice uses a full bridge setup, which provides active temperature cancellation and the maximum possible signal amplification.
Zhao Jin performed previous research into using piezoelectric sensors within the Curiosity wheels on the NASA Mars rover that launched in 2011. Using a lab-based testing rig, a rover wheel was passed over various terrains to train a support vector classifier to classify an unknown terrain type. Our project takes Zhao Jin's research further by investigating the use of strain gauges instead of piezoelectric sensors. We also changed the wheel design to the latest NASA Mars rover, Perseverance.
The original NASA JPL spoke maintains a uniform thickness in its outer two thirds. We modified this design with a continuous taper, progressively reducing the cross-section along its entire length with the idea of separating different frequencies via its stiffness gradient. We then pushed this frequency separation concept further with our discrete section design, 3 distinct thickness zones intended to act as individual mechanical filters for low, mid, and high frequencies. When we look at the FEA, looking at low frequencies, the original NASA spoke spreads strain out with a lower magnitude, making it difficult to isolate a clean signal. Both of our custom designs successfully concentrate this low frequency strain at the compliant lower bend. And at higher frequencies, strain migrates towards the hub for all the designs, although the abrupt thickness changes in the section design act as severe stress rises at the fillets, posing a potential fatigue risk. Ultimately, the continuous taper was the clear best choice. It separates frequency bands much better than the original spoke, and just as well as the more significantly modified section design, and it presents us with 3 clear strain concentration areas to mount our strain gauges to.
To validate our spoke design, we built this single spoke test rig. A 60% scale PLA spoke was printed at 0.08mm layer height with FDM and had 3 full bridge strain gauges bonded at locations derived from our FEA results. The hub side end was clamped to the metal desk leg, while the wheel side was fixed to an audio exciter, which itself was fixed to another part of the table leg with a vise. The audio exciter was driven with a sawtooth wave with a frequency sweep from 0 to 500 Hz. Strain data was recorded simultaneously across all 3 strain gauges using the ADS-1256 analog to digital converter, achieving 190 samples per second across all channels. The strain gauge readings were calibrated to 0 during the first few seconds of the script before the start of the frequency sweep. Now, looking at the frequency sweep results, gauges 1 and 3 show clear responses. Blue peaking across 2 windows around 100 to 160 Hz and 250 to 320 Hz, and green responding in the 10 to 100 Hz range and having even stronger signals from 210 to 300 Hz. Gauge 2, however, is virtually flat across the entire sweep. It's worth noting that 190 samples per second is low for detecting frequencies from raw strain data alone. However, since we're directly plotting the known frequencies we played through the exciter, this wasn't a limitation for this experiment. This gives us 2 insights. Gauge 2 is redundant, sitting at a bending node, so we dropped it for the full wheel test. And both active gauges show 2 sharp distinct resonant bands, more separation than the FEA predicted, possibly due to the desk leg's natural frequency coupling into our boundary conditions.
We needed to capture strain gauge data with a wheel on real terrain, and we decided this portable rig was the best approach. Because slip rings would introduce rotational noise to our signals, we kept all data collection components confined to the hub. A high-torque, low-speed motor drives the assembly for guarantee of constant velocity, and mechanically, we isolated the system using a free pivoting handle, meaning the normal force applied to the ground should stay constant. We can write to an SD card at 1,000 samples per second, ensuring we capture high-frequency signals, and it needed to be strong, so the wheel was printed out of one piece in ABS, and the wheel components are high-infill PETG.
Once we had recorded all the data from our field trip to the terrain testing areas, we downloaded the data and manually labeled it to correlate with our notes from the field testing. For each terrain type, we split the recordings by their peaks on one channel, indicating a full rotation of the wheel. Each of these peaks were used as markers to split the recording into segments, which were then used to form our test terrain dataset for our classifier. In order to perform feature extraction on the segments, a discrete wavelet transform was used with Debussier's 8 wavelet to extract the coefficients. These coefficients were then used to calculate the mean power per frequency band, which were the feature set for our classifier. Once we had built our dataset, we performed classification using a support vector machine and random forest. For our application, random forest classification obtains better results. Initially, we used 3 segments before testing, before switching to a stratified k-fold cross-validation with 3 folds due to our small and uneven dataset size. Our k-fold cross-validation had a mean accuracy of approximately 84%, showing that the classification was working reasonably well. This could be improved further with a larger dataset size and further refinements to the feature set. You can see a copy of our confusion matrix on the k-fold cross-validation on the right-hand side, with the terrains labeled with pictures, and you can see generally confusions are occurring between very similar terrains, which shows that generally our model is working as expected.
So what's gone well on this project? Well, in general, we consider the concept of using strain gauges for terrain classification fully validated. An accuracy of 80% across varied and realistic terrain conditions. We're really happy with that. Slippage detection is also an added benefit, and in our testing, all cases of slippage were detected. This potentially eliminates the need for torque sensors. And we built the setup with, surprisingly few hardware issues when we were testing it, which is always a win. We also succeeded in using the wavelet transform as a signal processing technique, which was taught to us during the module lectures. Consider the value of having multiple gauges in different strain concentration areas somewhat validated. We do note an extra of 10% when only one gauge is used. However, it is possible that strain gauges are so sensitive that if they're placed in the correctly informed position, they can detect the full range of frequencies needed. So potentially using multiple gauges is overcomplicating the system.
Within our project, there are a few limitations which we would hope to improve upon further when deploying in a real-world scenario. One of these was the inconsistency between the simulation and the actual exciter experiments. This could be due to the experimental setup, such as the natural frequency of the table. We also did not match the one-to-one correlation with the scale of the NASA Mars rover wheels. We'd also like to use an encoder approach rather than using a software approach for splitting the data into segments. Due to a limited time, we only have a small data set and would hope to gather much more data for the classifier. We also, in the real world, would mount the wheel on the rover rather than having this test rig we were using, which could potentially have some forces from us using the test rig. And we'd also want to try on more representative terrain types on Mars, such as combined terrain with sand and rocks, and also larger rocks that have been observed on Mars.
This project surfaced 3 key design engineering insights. First, simulation has real limits. Our FEA predicted frequency separation, but the real-world spoke test revealed more distinct resonant bands than expected, reminding us that boundary conditions in the physical world are rarely as clean as model assumes. Second, the project only came together because it drew on the full breadth of our degree. Finite element analysis, machine learning, signal processing from electronics, and manufacturing skills from physical computing and industrial design engineering all played an active role. Finally, we deliberately adopted an incremental approach, simulating first, isolating a single spoke to validate sensor placement, and then integrating into a full rotating wheel, ensuring each stage answered a specific unknown before new complexity was introduced. Thank you for listening, and now enjoy a little montage of us building the full rig.